And we know we'll have José Manuel Casas. Are you connected?
Yes. Can you hear me?
Yes, we can hear you. You can share your screen, and you will tell us about multi-frequency point source detection with fully convolutional networks performance in realistic microwave sky simulations. And we're waiting for your slides.
Yes, one moment.
Go ahead.
Okay. Here.
Very good. So you'll have,
Can you see the screen?
Okay. So you have 12 minutes. I'll warn you on Slack before 3 minutes and before 1 minute. Go ahead. Thank you.
Okay. Hello. My name is José Manuel Casas González. I'm a first-year PhD student in the University of Oviedo. And I would like to show you the results from our paper, Multi-Frequency Point Source Detection with Fully Convolutional Networks Performance in Realistic Microwave Sky Simulations. In this work, we have developed a mathematical model based on artificial neural networks to detect point sources in realistic simulations using Planck data. And we have compared our results against one of the most important multi-frequency point source detection methods, the matrix filters, which were used in the Planck collaboration. First of all, I will introduce the problem. After that, I will talk about the simulations and the methodology used. And finally, I will show the results and our conclusions. Well, the point source detection is one of the main issues for Planck's successors, such as PICO, the CMBS4, or the Simons Observatory, since they will have a higher angular resolution than Planck. And as we know, point sources are one of the main contaminants to the recovery of CMB signal at small scales. Therefore, we need to develop more accurate and reliable methods to detect them for the next CMB experiments. The traditional methods are filters, like the Mexican hot wavelet 2, which was used in the Planck collaboration. But this year, Bonavera et al. Developed a mathematical model based on artificial neural networks called PoSeIDoN to detect point sources in realistic single-frequency simulations. And they compare the results against the ones from the Mexican hot wavelet 2, obtaining better results than the filter, especially in the much lower number of spurious detections or false positives, as we can see in this figure. The multi-frequency point source detection is another issue for Planck successors because the actual point source detection methods are generally single-frequency methods, which can't deal with the fact, which can't deal with the spectral behavior of the sources. That is, they can deal with the fact that a point source in a map can be a totally different astrophysical object than the other point sources in the map. And when we do the component separation, which is a multi-frequency process, there are a lot of point sources which cannot be detected by the method. Therefore, we need to develop more accurate and reliable multi-frequency detection methods. Since we will have a machine learning model, we will need to train it. And to do that, we will use simulations about the microwave sky, realistic simulations using Planck data. Each simulation will have two different sets of images. The first one will have only the contribution from the point sources, which will be radio galaxies having more intensity for the lower frequencies, and infrared type galaxies having a higher intensity for the higher frequencies. The other set of images will have those contributions from the point sources added to other contributions acting as contaminants, such the cosmic infrared background, the cosmic microwave background signal, the diffuse galactic emission, more precisely the thermal dust, the thermal Sunyaeter lobes, the thermal Sunyaeter lobes from clusters of galaxies, and instrumental noise using Planck values. The patches will be at above 30 degrees of latitude to avoid the regions such as the galactic plane with higher galactic contamination. And the channels will be from now on channel 1, the 143 channel from Planck, channel 2 will be the 217, and channel 3 will be the 353 gigahertz channel from Planck. The methodology used is a fully convolutional network called PoSeIDoN, which works in 2 steps. The first one is a set of convolutional blocks, which make inference over the total input images, that is, the images with all the contributions. And through their feature maps, they extracts the more relevant characteristics from that images, comparing them with the point source only label images. The second step is a set of the convolutional blocks, which are added to the convolutional ones, and they make predictions about where the point source will be located and which will be their flux density. Therefore, the output from the neural network will be patches with cleaned patches of point sources. An example of an output from the neural network and from the matrix filters is shown in this figure. As we can see, both methods perform the detection of the brighter point sources quite well, but the neural network is performing more detections than the filter because the generalized error for the 3 patches is lower than for the filter. But however, to study the catalogs properly, we need to use different statistical quantities. For example, we have used the recovering of the flux density of the detections, as we can see it in the top figures. The channel 1 is represented in the left figures, and the channel 3 is represented in the right figures. We have used the completeness, as we can see it in the top panel of the bottom figures, and we have used the reliability of each model using the number of spurious detections or false positive, as we can see it in the bottom figures, in the bottom panel of the bottom figures. As we can see, both methods are recovering quite well the flux density of the detections, but the recovering of the neural network is better since it is adjusting to the most perfect case, which is the dotted black line. And for the higher frequency, the neural network is recovering better than the filter, the flux density of the fainter sources. That is, the neural network can recover better the flux density for lower flux densities, which is important for the next CMB experiments with higher angular resolution than Planck. For the completeness, we can see that for channels 1 and 2, both methods have a similar completeness, reaching the 90% of completeness level at lower flux densities than for the Planck collaboration, which is represented in this vertical dotted line. And for the third channel, we can see that the neural network has a higher completeness than for the filter, because the location of the point source is learned with the help of the other channels. For the reliability, we can see that the neural network is a more reliable model than for the filter, because the number of spurious detections or false positives is much lower in the 3 channels than for the filter. We have compared the performance of both multi-frequency and single frequency approaches. We can see that the multi-frequency approach is recovering better the flux density of the detections, especially the fainter ones. And we can see that the completeness is higher for the multi-frequency approach. That is, it is detecting more sources than the single frequency approach. This better performance is because 2 facts. The first one is that we are using a higher amount of total information to train a neural network, because we are using 3 channels instead of 1. And because the neural network is learning the different correlations between the astrophysical elements in the 3 channels. Our main conclusions are that neural networks can be the future point source detection methods in the next CMB experiments. And we can say too that the multi-frequency approach is better than the single frequency approach, both based on neural networks. But we have another conclusion, such as the lower computation time for neural networks, and that they have not the border effects as for the filters. And as a future prospects, we can study this performance in regions with higher galactic emissions, such as the galactic plane, based on the results for the higher frequency. And we can extend our study to do the CMB component separation to extract the CMB signal instead of the point sources signal. And that was all. Thank you for your attention.
Thank you. So you actually are in advance, so we have time for a few questions. Are there questions in the room? While people are thinking a bit, I have a few actually. So here you are not inputting any knowledge on the instrument, right? Your neural network don't know anything about the beams of the different instruments, because you're mixing here different observations which have a very different resolution, right? So this is learned by the neural network as well.
Yes, I don't know the characteristics of the instrument. I know that I am using different resolution. For example, the resolution in the first channel is different for the other two. But this is intentionally to study the performance of neural network with different resolution.
Okay. Another question. Can you go back to the slide where you were describing your simulations, please? Perhaps I missed something.
Okay.
Yes, so here you are at high galactic latitude, so you're taking into account some of the galactic emission. What part of the galactic emission are you taking into account here?
Based on the frequencies, we are taking into account only the thermal dust.
Okay, and here you're taking into account TSE as well, but are you also including clusters of CIB? I mean, non-resolved CIB, or are infrared sources only point sources?
Yes, we are using the emission from spheroidal galaxies as a continuous emission for the cosmic infrared background.
Okay.
Is in this patch of higher frequency it has this type of behavior.
Okay, that's interesting. And have you tried other experiments with different parameters, and how much you will need to retrain your neural network each time, or do you think that some of the training is transposable for different instruments with different systematics and different beams?
To do that, we need to do other simulations. Well, we can validate with other parameters, but to have a properly study, we need to train the neural network all the time.
Okay, thank you. Are there other questions in the room? I see none on Slack either, so I propose that we thank our speaker again with a round of applause.